Hello, brethren out there. For this particular session, we're going to talk about pure mathematics. Categorically, we're going to talk about logarithms. When we talk about logarithms, we're trying to talk about functions or indices that are expressed in exponential way or exponential expressive. So in this case, let's say we have 2 to the power x, which is equal to 8. If you have something like this, this is called an index. So this one is called an index. But if we have log, then we have 2, then 8 here, and then equals to x. This is a logarithmic equation. So in this case, we're going to find that we're going to talk about how best we can handle logarithmic functions and how best we can solve. Join me as I explain in detail how best these things can be dealt with. So we're going to find that when we are talking about logarithms, it's best advisable to understand how best you can express some index notation in form of logarithmic. So in this case, let's give up some examples. So say examples, let's say express in a logarithmic, express in a logarithmic form. Then here, 1, we have 2 to the power x is equal to 16. If we want to express this in a logarithmic way, we are going to say this is equal to, this is going to become log. When it becomes log, this 2 is a base. This x is an index, or it's called an exponent. So this base, which contains an index, should be able to come here as a lower base. Then this equated number here becomes that is our base here. Then what you are going to equate to is the actual power under which this was raised. So we are going to say like that. When we do like that, then it means this is a logarithmic expression, while this is an index expression. And this is how best we're supposed to do this. Suppose we have example 2. If we have, that is x to the power 3 equals 27. Then in this case, we are told to express in a logarithmic function. We are going to say log again, but this is the actual base in this case, despite being a letter. So we're going to say x, then this 3 is supposed to be equated, so this 27 will come before the equal sign, which is going to be equated to 3. So if there is something we should learn and understand and utilize, is that it is something that should be able to depict that this base will always be a base beneath the log. Then this power will always be the number to equate to, while this 27 will come before the equal sign. So log x 27 then equals to 3. These are just some of the examples we can use to express index notation in a logarithmic function. Then also we can be taught to express a log in terms of how best we can solve. So let's say we are trying to solve some logarithmic functions. Let's say we have examples here. Let's say solve for x in, then Roman numeral 1, we have log, then 2, then we have 32, which is equal to x. If we are taught to solve this logarithmic function, the first thing we need to do is to express it in form of an index notation. How can we go about that? This 2 is a base. So you're going to say 2, then this is a power, not this one. So this is 2 to the power x is equal to, then this is 32. Then afterwards, we're going to understand that 2 is a base, the same applies to 32. We are going to reduce the bigger number and express it in the smaller base. And thereby, we are going to say 2 to the power x, which is equal to. When we express 32 in base 2, we are going to assume how many times you can multiply that 2 to get 32, which we can say 2 times 2 times 2 times 2 times 2 times 2. So 1, 2, 3, 4, 5. 2 times 2, 4 times 2, 8 times 2, 16 times 2, 32. It is the one that is here. So this 2, for it to represent 32, it's supposed to be multiplied 5 times consecutively. So the bases are now considered the same. 2 is equated to 2. Therefore, x is equal to 5. Having done that, then it means we've solved, that is for x. And this is how best you are supposed to solve logarithmic functions. The first thing, always remember, express in index notation, then kindly solve only for such types of logarithmic function. Let's go to the second one. Let's say we have log x, then here we have, that is 27, then this is equal to a 3. So we're going to find that here, we're going to say this x is raised to the power 3, which is equal to 27. Afterwards, for this one, we're going to find that for us to solve, we have to ensure that we get rid of this 3. We can only get rid of this 3 by multiplying with a reciprocal, which is 1 over 3. In the sense that this 3 and that 3 will cancel, so that x is left alone, and that is our achievement. So we're going to say x to the power 3 times 1 over 3 is equal to 27. Then this is going to be to the power 1 over 3. Why am I saying to the power 1 over 3? It's because this 1 over 3 has been multiplied here. And there is an equal sign, which states clearly what's done on the left is equal to what should be done on the right. So I'm going to say this is equal to x equals, when we say 27 raised to the power, which is a fraction, we introduce a root. Then this denominator becomes the decisive root. Then this base comes inside there. Open, close brackets, then we put a 1 there. Then upon reaching this point, it simply means what number can you multiply 3 times to get 27? In this case, the answer is 3. But there is power 1 outside. So x is equal to 3 to the power 1 is 3 itself. Having done that, then it means we've solved such kind of problems that can involve logarithmic functions. So let's see for another example which we can kindly talk about. Then also sometimes we can also talk about the rules for logarithms. So we can be able to talk about the rules. Rule number 1 is about multiplication, which goes in hand together with addition. In this case, if we assume we have log, which is to the base of a, and then we have pq. This is assumed to be log a, then this is p. In as much as these are combined, it means you are adding. So I'm going to say plus. Then I'm going to say log, then a with q. So this is how best are supposed to do this. So whenever 2 letters or 2 numbers are combined under the same logarithmic, so long as the base is the same, it means you are adding 2 logarithmic type of expressions. And this can be proved, like if we have log, let's say this is maybe a, then we have, that is maybe 20 here. We can be able to write this 20 separately in the way that we can be able to maybe use certain 2 numbers we can use to multiply and get 20, which could be 4 and 5, 2 and 10, 5 and 4, and 1 and 20. So we can be able to say log, then a, then we're going to say here, we're going to say that is a 4, like that. So then we're going to say that is plus, then log a here, which is going to be a 5. The same way I've said that is the same way of writing 4 times 5. If something is given like that, where I had to put a 20, then if we have to express and write separately, then we have to write it like this. So the first law, or the first rule of logarithms states that when 2 numbers are multiplied under a logarithmic which contains the same base, it means you are adding the 2 logarithmic function. And this is how best we're supposed to put it. Then, let's come on to rule number 2. Rule number 2, we will talk about division, which will go together in hand with subtraction. So, let's say we have log, that is to the base of f, then this is p over q, like that. So I'm going to say this is log to the base of a, then this is p minus log to the base of a with a cube, like that. So whenever these are being divided, it means we are subtracting. In the sense that if we have log to the base of a, then we have 4 over 5, like that. Then this means this is going to be log to the base of a, we're going to have 4 minus log to the base of a with the 5 there. So this is the second rule. Then we're going to find that maybe the third rule can be able to talk about if we have log the base of a to the power that is a 1 or to 1. So log of the 1 is always assumed to be a 0. This is achieved in the sense that if there is this 1, because we always believe a number raised to the power is a 0, so the log of 1 is always a 0. Then we can talk about the fourth rule, where we can say if we have log to the base of a and a here, log of the same base is always a 1. So these are some of the rules we should be able to know if we are dealing with logarithms. So now, let's say we have some examples here. Let's say we have some examples here. Let's say the question says evaluate. Then we have 1. We have log 6, the power that is 36. So we're going to find that log 6 to the power 36. We're going to say the first step is to ensure that this 36 is reduced to a common number which will suitably be also seen to be like 6. So we are going to say log 6. Then where there is 36, we say this can be able to represent 6. So if this represents 6, how many times can this 6 be multiplied to get 36? It's twice. Then after doing that, this bar is supposed to come in front of the log. So it will be 2, then log, then 6, again another 6 there. But remember the fourth rule. We said the log of the same base is always a 1. So I'm going to say 2, but everything here will mean a 1. Then this is going to be 2 times 1, then this is just going to give a 2. Having done that, then it means this is the answer. On the same basis, we can be able to say, let's say we have that is log 2, then 64 here. We can be able to reduce this 64, thereby letting it become 2, using the rules we just recently talked about. So it can be log 2, then here we say that is a 2. But how many times can this 2 be multiplied to get that is 64? It can be multiplied 6 times. Where 6 times 2 times 2, 4 times 2, 8 times 2, 16 times 2, 32 times 2, 64. 1, 2, 3, 4, 5, 6. So we set to the power 6. But remember what we did in the first example? The power of this drops and becomes a coefficient of the log. So this is going to become 6, then log 2 of 2. And of which we are going to say 6. But this is the log of the same base, which we are going to say 1. And then this is going to become 6 times 1, 6. So this is how base we're supposed to evaluate. We've used the fourth rule. We can also apply the same rule maybe on the first rule. So let's say we have another example. Remember, we said log of a p cube. Remember what we did? We said this is going to be log a, then b plus log, that is a of q, like that. Remember that rule? So let's try to use it. So let's say if log 5, let me just say if log a of 5 is equal to 10 and log a of, that is 6, maybe is equal to 20. Then evaluates 1 log a of 30. So if we have log a of 30, it's very simple. Examiners are clever, so you just have to be critical thinkers in this case. So this 30 is achieved by having 5 and 6 being multiplied. So we're going to write this separately. If this is log A, then 30. It means these two numbers which are given are multiplied. So we're going to say this is the same as log A 5 multiplied by 6. And this 5 is here, this 6 is there. Then we're going to say this is going to be equal to log, then I'm going to say A of 5 plus, we're going to write separately. Remember what we did there? Then I'm going to say log another A, then 6. This addition is coming because you're multiplying. How did I get 5 multiplied by 6? I looked at my product. Then afterwards, I just have to go back and look at what I have to assume if I have achieved something. In the sense that log A of 5 is 10 and I've achieved log A5. So I need to replace 10. So I'll replace 10, then plus log A of 6. Log A of 6, if I've achieved it, I need to replace the 20. So I'll replace 20. So in this case, it's 10 plus 20, which becomes 30. Like that. So this is the correct answer. And this is how best we're supposed to understand it. Then, if we are being able to have, that is log A, then we are going to have, that is maybe in the brackets here, log A of 1.2. So in that case, if we have 1.2, it means this number cannot be gotten by multiplication. It was gotten by division. It's either 5 was divided into 6, 6 was divided into 5, whichever way. So we're going to drop down here. So we're going to say log A. So this is the same as 6 over 5. Let's try to prove 5 into 6. So 5 into 6, 1. Remainder 1. So we're going to put the point, we add the 0, 5 into 10, that's a 2. So that's the number, so that's what they did. But remember the rule? The rule was that if these are divided, then if we have to write separately, it means if we are subtracting. So we are going to say this is going to become log A of 6 minus, then I'm going to say log A of 5. But remember, once you reach that stage, you just have to substitute. Log A of 6, the value is 20. Then here, where there is division, it was more like subtraction, so minus log A of 5, I'm going to put that is a 10. Then I'm going to say 20 minus 10, and the answer is a 10. Having done that, then it means we've talked about the first and the second rule. And that's how best we can be able to know. We can be told to solve logarithmic equations. But when we talk about logarithmic equations, there are such types of equations where you cannot be able to solve them using an index way of expression. So here we're going to say, let's say on Roman number 1, we have 4 to the power x plus we have 2 to the power x times 3, which is equal to, that is a 4. The first thing we have to do and understand is that this cannot be solved using an index way of solving, in the sense that this 3 cannot be reduced to base 2. Then this 4 we have here cannot also be reduced, that is, to base 2, in the sense that this 3 cannot. So here we are going to say 4 raised to the power x can be reduced to 2. Then we are going to say when this represents 2, it's supposed to be with power x. But remember, this 2 is being able to be multiplied twice. So before putting power x, we can be able to say power 2, then combined with the x. Then plus 2 power x, then I'm going to say times 3, then which is equal to, that is a 4. Then upon reaching this stage, we're going to say 2 to the power 2x, 2 to the power x, then is equal to 4. Where there is 2 power x, we're going to replace with a p. So I'm going to say let, that is 2 to the power x, be equated to n later. So if we have to remove these 2, then we have achieved 2 power x. But there was power 2 here, which means whatsoever you're going to replace will be a square. So where there is 2 to to the power x, we are going to replace with a p. But there is power 2 here. So we say p squared plus. Then this is just a p, then times 3 is equal to 4. Then this is going to be p squared, then plus 3 times p is going to become 3p. Then if we cross this over, this is going to become negative 4. Everything will be equated to 0. Now we have our quadratic equation which we can solve using product, sum, and factor. Then here we're going to say p squared minus plus 3p minus 4 is equal to 0. So we are going to find the product, the sum, and the factors. So when we talk about the product, we're supposed to multiply the coefficient of the variable with the highest power, which is power 2. And the coefficient here is the hidden one. 1 multiplied by a constant. It's going to give negative 4. Then for the sum, this is the coefficient of the middle that is variable. And the middle variable is just p with a coefficient of 3, which is positive. So the coefficient is 3. The factors are two numbers which, when added, should be able to give us the sum. When multiplied, should be able to give us the product. So the two numbers are negative 1 and a 4. Such that negative 1 multiplied by 4 is negative 4. Negative 1 plus 4 is going to give positive 3. Then let's replace these values. So I'm going to say p squared. Then, if you want to replace the 1 in an expression where you're using variables, you replace with only a single variable. So we will say minus p plus 4p. Then we're going to say minus 4, everything equated to 0. Then we're going to group the terms like this. So we're going to say p, open brackets, this is going to be p minus p into p, 1, then plus. Here we are going to factor out 4, then 4 into 4, 1, leaving a p, minus 4 into 4, 1, then is equal to 0. Then we're going to say p plus 4 equals 0, or p minus 1 equated to 0. Then we're going to say this is p plus 4, which we're going to say p is equal to 0 minus 4, so p becomes negative 4. So this is our answer. Then here we're also going to say p equals 0. This is negative 1, so plus 1. This is going to be p equals 0 plus 1. This is going to become a 1. So these two values are the one we are going to use to find the value for x, which was the actual variable in our expression. And how can we find that? We made a temporary expression which we said let 2 power x be equated to p. So we are now going to find the answer. So we will say for p is equal to 1, we're going to say 2 to the power x is equal to p. In reference to the statement above. So I'm going to say 2 x is equal to, where there is p, I'll replace 1. Then I'm going to say 2 x, which is equal to any number that gives a 1, or if we have an answer which is a 1, it means a certain number was raised to 0. Now that we have 2 to the power x, it means there was a 2 raised to the power 0. In the sense that 2 to the power 0 gave a 1. Then the bases are the same here, so I'm going to say x equals 0. Then for this one, which is p to the power negative 4, the log or the answer is going to be invalid, because the log of an answer which could be negative, or for any like evaluated variable which is negative, the log or the answer for any variable is invalid. So if we say 2 to the power x is equal to negative 4, we're going to say this is invalid. So the only correct answer is x to the power, or x equated to 0, which we achieved by saying where there was 1, there is 2, and I'm only picking 2 because there is a base of 2. If there was a base of 3, I would have picked that is a 3. So 2 to the power 0, then this one can be able to give a 1. So what was more important is that from this expression, 4 to the power x, you reduce it to the power 2x. So to the power 2, then it's been able to be, that is correct. Then you maintain the actual exponent that was there. Then 2 to the power x times 3 here. Then you select 2 to the power x be equal to p. You can equate to n later. You can pause the video, kindly rewatch, and grab a paper so that you can be able to ensure self-reliance in whatsoever this kind of problems can be able to be experienced in your academics. And also, let's look at example 2. So, on example 2, let's say 9 to the power x plus 3 to the power x, then times negative 9 equals negative 18. Then if we are told to solve for this logarithmic function, we are going to reduce according to how we know. We are going to say here, we are going to reduce 3, but this 3, as long as it is representing 9, it's supposed to be raised to the power 2 with x plus, this is 3 to the power x, then multiplied by negative 9. Everything is equated to negative 18. Then we are going to say let's 3 to the power x be equated to p. So where there is 3 to the power x, we are going to replace with p. So 3 to the power x is p, but 3 is raised to the power 2. Meaning, if we had 3 to the power x, we are supposed to directly replace with a p. Now that there is power 2, it means this is going to be squared. Then plus, we're going to say 3 power x is also a p, multiplied by negative 9, equated to negative 18. Then I'm going to say p squared. Then I'm going to say positive times negative, negative 9. Then with p, then if we cross over negative 18, it's going to be plus 18. Everything equated to 0. Upon reaching this stage, we are now going to solve using the product, the sum, and the factor. So we have p squared minus 9p plus 18 equals 0. So I'm going to find the product, the sum, and the factor. So when we talk about the product is when two numbers are being multiplied and the number is the coefficient of the variable with the highest power and the constant. So 1 times 18 is 18. Then for the sum, this is the coefficient of the middle variable. The variable here is p, but the coefficient is negative 9. Then we're going to find two numbers such that when we add, we're going to get negative 9, which is the sum. When we multiply, we're going to get that is 18. The numbers are negative 3 and negative 6. Such that negative 3 plus negative 6, we evaluate getting negative 9. Negative 3 times negative 6, we get positive 18. Let's kindly replace. So I'm going to say p squared minus 3p minus 6p plus 18, everything equated to 0. Then let's group the terms. So I'm going to say what's common in this bracket is p. Then p into p squared, we're going to leave, or we are going just to evaluate a single p. Then minus p into p, it cancels, leaving a 3. Minus, then here we're going to say what's common is 6. Then open brackets, here there is going to remain a p. Negative times positive, negative. 6 times 18, or 6 into 18, we're going to get that is a 3. Equated to 0. Then I'm going to say p minus 6 or p minus 3 equals to 0. Then I'm going to say p equals 0 plus 6 or p equals 0 plus 3. Then the first answer is p equals 0 plus 6, it's positive 6, or p equals positive 3. The answers we just evaluated simply give us, that is the value of p. But remember, in our equation, there was the variable which is x. So we're going to turn back to where we expressed this as an assumption. We said, let 3 to the power x be equated to p. So we're going to solve. We're going to say for p equals 3. We're going to say 3 to the power x equals p. So we're going to say 3 to the power x. Where there is p, we're going to replace with a 3. So if you replace a 3, the bases are the same now. So I'm going to say this is 3 to the power x. This is 3 raised to the power 1 because it is there once. Then the bases are the same, so we can assume x is equal to 3. So this is the first answer. Then we're going to say for p equals 6. We're going to say 3 to the power x equals to 6. Remember, this cannot be solved using the exponential index way of expressing or solving, we are going to introduce common logarithms. When we introduce common logarithms, it's going to be very simple. So we are going to say if we introduce the common logarithms, then we are going to denote them as LG, 3, then X, which is going to be LG, then 6. Then this as a power is supposed to fall in front of the log. So this power becomes a coefficient. So it's going to become X log 3 equals log, that is 6. Then our interest is to find X. So I'm going to divide by log 3. Then I'm going to say log, that is 3 again here. So that and that cancels. So finally, we are going to evaluate using a calculator, where we're going to say log 6 divided by log 3. And on the calculator, it's being able to give 1.63, and the numbers keeps on recurring. So we are going to give the answer correct to 2 decimal places, where we're going to say this is going to become, that is 1.63. So these are the correct answers. So here, what there is 2, we are just going to put 1. So I'm going to say 3 to the power x, which is 3. This is supposed to be a 1. Then 3 to the power x, which is equal to 3 to the power 1. So the places are the same. So x becomes a 1. Then 3 to the power x, which is a 6. This 6 cannot be expressed in plus 3. Hence, we can only use common logarithms, where we are going to have log 3 to the power x, which is log 6. Drop this power in front of the log, then divide with log 3 by using the both sides of the equation. Then the answer is x equals 1.63. This is how best we're supposed to evaluate this. Lastly, we can be able to talk about common logarithms. So, when we talk about common logarithms, we are trying to solve expressions which cannot be solved in form of exponential functions. So, let's say we have some examples here. We have some examples. Let's say we say solve for x in, then 1. We have, that is 2 to the power x equals 7. Before we draw our attention to this, let's start by solving it in exponential way. Let's say 2 power x equals 8, and like this. So 2 power x equals 8, it means this 2 is relative to 8, in the sense that this 8 can be reduced to 2 being a base. And how? We're going to say 2 to the power x equals, this is going to become 2 to the power 3. Then this is 2, and then this is 2. So the bases are the same, we consider the powers to be the same. So if these were indices, we would have achieved our answer in that easy form. Now here, we are going to be using a calculator. And in the sense that 2 power x cannot be reduced as 7, which can be due to a certain exponent. So we are going to say 2 to the power x like this, which is equal to 7. We introduce common log. So we say log, we are not going to write in full, just say LG, then 2 and x, which is equal to 7. So this 7 should also contain a log, because we've introduced it on the left, so should it be introduced on the right. So LG. So upon reaching this stage, if this was just a letter and this wasn't there, we would have divided. But because there's a power, drop this power so that it becomes the coefficient here. So it will be x, then log, then 2 equals log, then 7. Our interest is in finding x. So we are going to ensure that we divide by log 2 both sides of the equation. So over log 2 over log 2, like that. So log 2 and log 2 cancels. So x equals. We are just going to use a calculator and evaluate. So we're going to say log 7, then divide by log 2. So it's giving, that's 2.8073, so on and so forth. We are going to round correct to 2 decimal places, which will become 2.8. But getting this as the second figure follows with a 7, which is way above 5. We just pick a 1, add to the previous number. So this becomes x equals 2.81. And that is the correct answer. So this is for the first one. So my main encouragement is make sure you grabbed a paper while watching this video, pause where relevant, and be able to kindly rewatch. So let's solve for another one. So that was the first one. Let's say we have another example. Let's say we have 3 to the power x minus 1 equals 8. So if we have such kind of an expression, let's look at this base. This base is 3. This should force 8 to become or to be reduced to base 3, which it can't. So we're going to introduce common logs. So I can just say introducing common logs gives. So here I'm going to say LG, then 3x minus 1 equals another log, then 8 here. I'm supposed to drop x minus 1 to the front of the log. So I'm going to say x minus 1, open close brackets because x is not alone. Then log, then 3 equals log, then 8. My main area of interest is to ensure that I find that is log 3, which I can't just easily divide with. So I have to ensure that this log 3 is being multiplied by x and also multiplied, that is, by 1. So I'm going to say x multiplied by log 3. We're going to find that this is going to become x log 3. Then negative 1 times log 3, negative log 3 equals log, that is 8. My main area of interest is to find x, so log 3 is free to cross over the equal sign. So I'm going to have x log 3 equals log 8, then this is negative, plus log, that is 3. Then this is going to become x log 3 equals, we're going to, x equals log 8 plus log 3. So before finding the answer, I can now divide with log 3. So I'll say divided by log 3, divided by log 3. So this and that cancels, so x finally equals. So we're going to say log 8 plus log 3. So log 8 plus log 3 is giving 1.3802 11242 over, we're going to divide it by log 3, which is 0.477121254. So then we're going to evaluate the final answer. So log 8 plus, I've only written those values for confirmation. Log 8 plus log 3, then divided by log 3. So the answer is given, that is 2.89. So this is the correct answer. And that's how we should be able to ensure that we are able to get the final answer. So 2.89 is the correct answer. And that's how we're supposed to evaluate such kind of logs. Then on the example basis, our last example is going to be, let's say we have 5 to the power x plus 1 or x minus 1 equals, maybe let's have 11 to the power, that is x. If we are told to evaluate and find or solve for x for such kind of a logarithmic, here is the way we are just going to handle this type of equation. We're going to introduce, so we'll say introducing common logs gives. So here we're going to say log 5, then x minus 1. Then here we're going to have log, then 11, then with an x here. Then we're going to say this x minus 1 will drop as a coefficient in front of the log. So it will be x minus 1, then this is going to be log, then this is going to be 5, then x will drop here, then this is going to be log, that is 11, like that. Then afterwards, we are going to multiply this log 5 with x and negative 1. X times log 5 becomes x log 5. Negative 1 times log 5 becomes negative log 5 equals, we are going to get x, then log 11. Upon reaching this stage, we are going to collect like terms together, which is x log 5 and x log 11. So we are going to say x log 5 is going to cross over x log 11. So I'm going to say minus x log 11. Then this is going to be equal to log. When log 5 crosses over the cosine, it was negative, so it will be positive. So this is going to be log 5. Then we are going to factorize. What is common here is x. Then I'm going to say log 5 minus log 11. Then I'm going to say this is equal to log 5. So our main area of interest is to find x. So we will divide with log 5 minus log 11. Then over log 5 minus log 11. So that and that cancels. So x equals, we are now going to evaluate and see what follows. So I'm going to say log 5. So say log 5 equals 0.69897000, then 4. Then over, we have log 5 minus log 11. So this is giving negative 0.3424, then 2268. Then we're going to divide. We're going to say 0.6 divided by negative 0.3. So we're going to say log 5. So we say log 5 divided by log 5 divided by, so 0.6989700004 divided by 0.34222268. So the answer is given negative 2.04. So this is the correct answer. X equals negative 2.04. So what's more important and apparently important is that believe in yourself, keep on revising, keep believing you can do it only through self-reliance, which can be gotten through proper practice and investing your time in everything that is relevant. For now, till next time, it's a goodbye.